Back student. Now today we'll discuss on atomic packing factor of BCC structure. Now we know that the metallic crystal structure basically have four types: that simple cubic structure, body center cubic structure, face center cubic structure, and hexagonal closed pack. Okay, there are four metallic crystal structure are there: SC, BCC, FCC, and HCP. Now atomic packing factor. Atomic packing factor for calculation of BCC, body center cubic structure, that we know that for BCC structure basically there are 8 atoms in 8 corners and in the and one center atom in the body on the cube structure. Okay, this is called body center cubic structure. Now you know that the atomic packing factor is basically the ratio is the ratio, okay, between the volume of atoms per unit cell divided by APA, volume of atom per unit cell divided by volume of unit cell, total volume of unit cell. So volume of atoms, total number of atoms of volume divided by volume of unit cell. Okay, now what is the exact number of atoms per unit cell that are basically for in case of body center cubic structure, that is basically 2. How it is? Now for body center cubic structure, as we know, there are 8 in basically there are 8 atoms and 8 corner there. That not means that actually that 8 atoms are exit or it's basically in your total BCC, one single BCC structure. So that means in body center cubic structure they share 8 atoms, one in each of 8 corners. So basically body center cubic structure is like that. So in 8 corner atoms are there. 8 corner atom they share with the besides BCC structure also. So this way. So one atom share here also, one atom this share in this portion also. So in this manner you can draw here. So what you see there, suppose this is your unit cell, one unit cell of BCC structure. What you see that 8 corner atoms, these 8 corner atoms can share this side, this side, this side, this side. So 8 corner atoms share with 8 at 8 sides. So that means 8 into 1 by 8 plus 1 body center cubic, 1 atom in each center. That is now sharing at all. Okay, so that means in addition to 1 atom and body center, therefore the total number of atoms in body center cubic structure, that is for 1 plus 1 equal to 2. Okay, and you know that already we are discussed on that the lattice parameter, the relationship between the lattice parameter, that is A actually, or the edge length, or that is the length between the two distance. So it is basically A with the atomic radius. The relationship is that R is equal to A into root over 3 by 4. Okay, R is equal to A by root 3 by 4. Now therefore the volume of 2 atoms, so there are only 2 atoms actually in a total volume of one unit cell BCC structure. Only 2 atoms are there, 2 fully atoms are there. So other portion are basically blank, right? Now just imagine that. So therefore volume of total 2 atoms, which atoms radius is R, that is you can calculate small v, is equal to 1 atom volume is 4/3 pi r cube. So 2 atoms volume will be 2 into the 4/3 pi r cube. So R is equal to, you know that, A by root 3 by 4. So write down in terms of R. So R is equal to this one, is equal to pi a cube by root 3 by 8. Okay, Now, you know that atomic packing factor is the total number of atoms, total volume of atoms divided by volume of one unit cell. So total volume of unit cell, if the distance between two atoms, or the distance, the edge length or the lattice parameter is a, then the total volume of one unit cell will be v is equal to a cube, as it is shape of cubic shape. So v is equal to, capital V is equal to a cube. Now total number of volume of atom, that is basically pi a cube by root 3 by 8. So that is v. So write down in terms of v here. And total v is your aq. So aq will be cancelled out. And so APF means atomic packing factor for BCC crystal structure, that will be 0.68. Okay. And for simple cubic, that is 0.52 or 54, I think 52. Okay. Now, in your semester is very much important for this question. So in the semester they will be asked for either in terms of MCQ, or the proof will be coming in your semester questions. So what is the atomic packing factor for BCC structure, what is the atomic packing factor for FCC structure, or prove that the FCC atomic packing factor of FCC structure is at 0.74 or 0.68, like that. Basically the number carries around 3 to 5 marks also, or it can be in terms of 1 marks MCQ also you can get from that portions. So this is very important chapter, important topic for its materials engineering purposes, because there is only a structure, crystal. This is the important. This is the basic fundamental part of that subject. Okay. Now for FCC, when you calculate the atomic packing factor for FCC, means face center cubic structure. So as the name suggests, that face center cubic. So basically cubic shape, that means 8 corner 8 atoms. So 8 corner 8 atoms, that doesn't mean that total 8 atoms are in this one unit cell. So they basically share with 8 others share other atoms also, unit cell also. Okay. So for face center cubic, so in each face, in cube shape there are 6 faces are there. In cube shape there are 6 faces. Suppose this is your cube. So you just imagine yourself that a cube are basically 1, 2, 3, 4, 5, and behind is a 6 face. So in 8 corner 8 atoms, and in each face of the cube shape 1 atoms are there. So that is called face center cubic structure. Now the important question is that what is the total number of atoms? Because you know that in 8 corner 8 atoms, and in each face of the atom in face center cubic is not in one unit cell. They share with the other unit cell or besides unit cell. Okay, they share. So actual number of atom, the total number of atom per unit cell is 4. How do you calculate? So 8 corner 8 atoms, that is share with 8 corner. So that is basically in case of face center cubic, they share 8 atoms, 1 in each of its 8 corner. That means 8 into 1 by 8. In addition, 1 atom in the center of its each face. So in 1 atom each center of its each face, and there are 6 atoms at the face center. You know that there are 6 faces are there, so 6 face atoms are there, and they can share. Okay, and each since every face of the cube is shared by 2 such cube, so this share portion will be in the upper part. This face is shared by the other cubes, this face shared with the other 2. So 6 atoms are shared with the 2 cubes. Okay, so 6 into 1 by 2. So that means 1 plus 3 is equal to 4. So total number of atom for this case is 4. Now in the previous lecture video, from that point of view, that the relationship between the radius and atomic radius of atomic radius and the lattice parameter relationship is that r is equal to a by root 2 by 4. Okay, so this is the relationship, as you know that. Now the effective volume of total number of atom, that will be, now the next part will be that volume of volume of 4 atom. Actually basically the total number of atom is 4, that's why it's 4 here. So volume of 4 atom with radius of r, that is equal to 4 into 1 atom volume is 435 r cube, so 4 atom will be 4 into 435 r cube. So 4 into 4 third pi, as you know that r is equal to a by root 2 by 4. The relationship is that we already proven that r is equal to a by root 2 by 4. Just write down in terms of r is equal to a by root 2 by 4 here, and after calculation you can get phi a cube by root 2 by 6. And so is a 1 unit cell are there. So 1 unit cell, the distance between two atoms is basically, or edge length is a. So cube shape, if the size of the length is basically a, so the total volume of a cube, that will be a cube, no doubt about that. So you know that atomic packing factor is the ratio between small v divided by capital P. Small v is nothing but the volume of atom, total number of volume of atom in unit cell divided by total unit cell volume. So that will be atomic packing factor for, so that is coming out from that portion. Small v here, write down here small v here, and capital V is a cube. So after you calculate a q will be cancel out. After calculation you can get 0.74. So atomic packing factor for FCC crystal structure is 0.74. okay. On the next day we will discuss on the atomic packing factor calculations of HCP, that is basically hexagonal close pack structure, and we can discuss on Miller indices. Okay, we can discuss Miller indices in the next lecture video. Okay, thank you very much for listening me and watching me. Goodbye.